Good morning to one and all. Today we are going to discuss about the abrasive jet machining. In this case of abrasive jet machining, we are going to use a jet of inert gas consisting of very fine abrasive particles strikes the workpiece at very high velocity, usually in between 200 to 400 meter per second. As a result of this, the material removal rate is occurs in the form of chips or erosive action on the surface of the workpiece. This erosive action has been employed for cutting, cleaning, etching, polishing, and deburring processes. This method of material removal is quite effective on hard and brittle materials like glass, silicon, tungsten, ceramics, etc. But not so effective on soft materials like aluminum, rubber, etc. It can produce fine and complicated details on the parts made of very brittle materials. So, the main purpose of this abrasive jet machining is mainly used for cutting or other operations on brittle materials. In case of the conventional machining process, the machining of brittle materials is very difficult process because because of its brittle nature. If there is a direct contact, as there is a direct contact between the tool and workpiece, a large amount of force is acting on the workpiece. Because of this one, the material may break or it's a or some other problems will come into the picture. But as because of this average jet machining, we are not going to get such type of problems while cutting or machining or any other machining operations on brittle materials. This is the schematic diagram of the abrasive jet machining. Here, first one, this rectangular box is the compressor, and this compressor is having one relief valve and air filter come dryer. By means of this air filter and dryer, and the compressor will absorb the air from the atmosphere. While absorbing the air from the atmosphere, it will filter, and if any humidity is present or any water drops are present in the air, it will be drier before entering into the compressor. And this is the pressure gauge. By means of that we can measure at what one at how much amount of pressure, with how much amount of pressure we are going to supplying the air to the machining setup. We can, by means of that we can see that one. And this one is the opening valve, or it can be used to open or close the valve, so that whenever we open this valve, automatically the high pressure gas will move from compressor to the abrasive mixer. Whenever it is closed, it is not it won't pass from compressor to the air abrasive mixing chamber. And this one is the opening valve and the pressure regulator. Based upon the requirement of the pressure, accordingly we are going to opening this valve, and accordingly at that much amount of pressure, air will enter into a mixing chamber. So this square shaped box is the mixing chamber. The main purpose of this mixing chamber is to mix the abrasive particles and air properly, so that it will be uniform. The abrasive particles will be uniformly distributed, and whatever the air and abrasive particles are mixed over here, it will be enter into the nozzle, and from the nozzle it will enter into the on the surface of the workpiece. The main purpose of this nozzle is to convert the pressure energy into the kinetic energy. Means the kinetic energy of the air abrasive particle mixture will be increased. The gap between this workpiece and nozzle is called standoff distance. And this workpiece is placed on the fixer. So the main components over here is the compressor, pressure regulator, control valves. These are the control valves. This is the mixing chamber, and this is the abrasive feeder. From here, we are going to supply the abrasive particles. From the air mixing chamber, we are going to supply the air, and abrasive particles is supplied into the nozzle, from which we are going to supply onto the surface of the workpiece. And because of this air and abrasive particles, material removal rate comes into the picture on the surface of the workpiece. Coming to this, the main components of this abrasive jet machining. The first one is the gas propulsion system. The gas propulsion system supplies clean and dry gas. It may be the gas may be like air, nitrogen, or carbon dioxide. So these propulsion system supplies the clean and dry gas to propel the abrasive particles. The gas may be supplied either by a compressor or from the cylinder. In case of the compressor, air filter cum dryer should be used to avoid the water or oil contamination of the abrasive powder. So if any oil or humid water particles are present in the air, that air will be the particles will be properly cleaned and dried before entering into the compressor. The gas should be non-toxic. It should not be toxic one. It should be available very cheap and abundantly available in the either in the market or in the atmosphere. It should not excessively spread when discharged from nozzle into the atmosphere. Coming to the abrasive feeder, this abrasive feeder is required. The required quantity is the main function of this abrasive feeder is the required quantity of abrasive particles is supplied by the abrasive feeders. So for the machining of any brittle materials, we need to supply the air and abrasive particles in a proper quantity. We have to mix this air and abrasive particles in a proper quantity. So those according to the requirements, these abrasive feeder will supply the abrasive particles into the mixing chamber. In this particular setup, the abrasive quantity is controlled by inducing the vibration to the feeder. The particles are propelled by a carrier gas to a mixing chamber. So whatever the abrasive particles are moves from abrasive feeder into a mixing chamber. The air and abrasive particles mix and move further into the nozzle. The nozzle imparts high velocity to the mixture, which is directed at the workpiece surface. Material removal occurs due to the erosive action of the jet of the air abrasive mixture impinging on the surface of the workpiece. So whatever the air abrasive particle mixture is properly mixed in the mixing chamber, and afterwards it is going to transfer to the nozzle. The main purpose of this nozzle is it converts the high pressure into a high velocity. The velocity of the air and abrasive particles is increases. With this high velocity, abrasive air and abrasive particle is impinges over the surface of the workpiece. And because of this one, the abrasive particles touches the surface of the workpiece, the erosive action will be takes place. Because of this erosive action, a certain amount of material is removed from the work surface. Coming to the mixing chamber, the mixing chamber is well closed so that concentration of the abrasive particles around the working chamber do not reach to the harmful limit. The machining chamber is equipped with a vacuum dust collector. A special consideration should be given to the dust collection system if the toxic materials like beryllium are being machined. So wherever there is a machining chamber, there a huge amount of dust will be generated during this machining process. It may affect the operator's health, and sometimes whenever we are going to machine some toxic materials like beryllium, it is very difficult for the operators to work over there. So that a special care like vacuum dust collectors and special consideration should be given to the dust collection system. Coming to this abrasive machining setup and AZM nozzle, the AZM nozzle is usually made of tungsten carbide or sapphire. The usual life of this tungsten carbide nozzle or sapphire nozzle is 300 hours. After 300 hours, we have to replace this nozzle. And this material, whatever the nozzle, may be tungsten carbide or the sapphire, it may having high resistance to wear. That's why we are going to use as a nozzle material. And this nozzle is made either a circular or rectangular cross section. And this nozzle is so designed that a loss of pressure energy due to the bends, friction, etc. is minimum as possible. The nozzle pressure is generally maintained in between the 2 to 8.5 kg per centimeter square. Its the pressure value is depend upon the material of the workpiece and desired characteristics of the machined surface. Means whatever the surface finish we required and accuracy is required and material to be machined. Based upon all these components or parameters, we are going to decide on how much quantity of the pressure we have to maintain while supplying from abrasive mixer to the nozzle and from nozzle to the workpiece. So with the increase in the wear of the nozzle, the divergence of the jet stream increases, results in more stray cutting and high inaccuracy. So whatever the slot, it may be a circular cross section, it may be rectangular cross section is there inside this nozzle. If it is wear, means it will undergo more wear, automatically it will become the out of shape. Whenever it will become out of shape, automatically the straight cutting action will not be takes place. Automatically stray cutting action will be means it will flow in the sides also. So that automatically the high inaccuracy is coming to the picture. The stray cutting can be controlled by the use of masks made of soft materials like rubber or metals for more accurate works and sharp edge definitions. The masks covers only the part of the job where the machining is not desirable. So wherever we do not need any machining, so there we are going to apply these masks. And this is the aluminum oxide. This is a Al2O3 silicon carbide SiCOC and glass beads, crushed glass and sodium bicarbonate or some of the abrasives are used in abrasive jet machining. The selection of these abrasives depends upon the type of work material, material removal rate, and machining accuracy is required. So aluminum oxide is good for cleaning, cutting, and deburring, while the silicon carbide is also used for similar applications, but for harder work materials. So finally, the silicon carbide is used for the machining. Abrasive silicon carbide abrasive particles are used for working hard work materials, and aluminum carbide is good for cleaning, cutting, and deburring. For obtaining the matte finish, glass beads are good. So whenever you require a matte finish type, then we can use this glass beads. But this crushed glass performs better for giving sharp edges. So wherever you require sharp edges, then we can use this crushed glass. However, cleaning, deburring, and cutting of soft materials are better performed by the sodium carbonate. So these sodium carbonate abrasives are used for cleaning, deburring, and cutting of the soft materials. The size of the abrasive particles available in the market range from 10 to 50 gram, and small abrasive particles are used for cleaning and polishing, while the large abrasive particles are used for perform better during the cutting process. So fine grains are less irregular in shape, hence their cutting ability is poor. So if the grain size is less or the very fine grains, then automatically they are less in irregular shape. So if they are less in irregular shape, automatically their cutting ability is also poor. Coming to this parametric analysis in abrasive jet machining, the important parameters that affect the material removal rate during abrasive jet machining are number is one is the standoff distance or nozzle tip distance, and this is the distance between the nozzle tip and the surface of the workpiece, and the type and size of the abrasive particles, what type of abrasive particles, and what is the size of the abrasive particles, and flow rate of the abrasives, gas pressure, work materials, and feed rates. So these are the different process parameters. It will affect on the performance of the abrasive jet machining. The effect of these parameters on the process performance are discuss in the next slide. Now coming to the what is the effect of standoff distance on metal removal rate on surface limits. The effect of change in standoff distance on the metal removal rate as well as linear metal removal rate is shown in the figure 2.2. See here, the standoff distance is taking on the x-axis and metal removal rate and penetration rate is taking on the y-axis. So when the standoff distance is increasing from 0 to 12, then automatically the metal removal rate is also increasing accordingly. If you still increase the standoff distance from 12 to 24 mm, then again the metal removal rate means the distance between the tool, that is the nozzle and the workpiece is increases, then automatically the effect of these abrasive particles will be reduced so that automatically the metal removal rate is going to reduce. And this penetration rate also, when the standoff distance is less, automatically the penetration rate is very less at the point 0. Then when you increase the standoff distance, then automatically the penetration rate is also increasing. At 8 mm, the penetration rate is very high. If you still increase the standoff distance, then automatically the effect or the capacity of these abrasive particles or the velocity of abrasive particles will be reduced so that the penetration rate is also coming down. And this is the relationship between the standoff distance and shape of the machined cavity. So if the distance between the standoff distance and surface of the workpiece, this is the nozzle tip distance and this line is the nozzle tip distance and diameter. This is the diameter 0.18 mm diameter of the nozzle. So sorry. So if there is a less nozzle tip distance, okay, automatically the straight cutting will be takes place and more depth. Also the diameter is also very good. So if it keep on increasing from 0.031 to 0.17 mm, 0.394 and 0.590 like that, if the nozzle tip distance is increasing, automatically see the diameter, the stray cutting is coming to the picture. Means exactly we are not going to get the precise shape and size. So that we have to maintain a constant gap of 0.031 mm with a diameter of 0.1 mm. So if you want to cut a 0.018 mm diameter, we have to maintain 0.031 nozzle tip distance. So if you keep on increasing, then automatically the stray cutting is coming into the picture. So the same in a range of standoff distance, which is usually varies in between 0.75 mm to 1 mm. So the distance between the nozzle tip and the workpiece is varies in between 0.75 mm to 1 mm. The metal removal, in this condition, the maximum metal removal rate we are going to get. As decrease in standoff distance improves the accuracy, it decreases the kerf width and reduces the taper in machined groove. That is showing 2.4. However, light operations like cleaning, frosting, etc. are conducted with a large standoff distance like 12.5 mm to 75 mm. Means whenever you require, if you want to do like a cleaning operation or if you want to remove the ice from the frosting operation, etc., then we can maintain more gap between the nozzle tip and the workpiece. That is the standoff distance. It may be like 12.5 mm to 75 mm. Now coming to the abrasive flow rate. How this abrasive flow rate will affect on the surface on metal removal rate. This metal removal rate is increases only up to certain extent, only up to certain value of the abrasive flow rate, beyond which it starts decreasing. See this diagram. See the metal flow abrasive flow rate is 0 increasing from 0 to 28. So when it is increasing from 0 to 4, 4 to 8, 8 to 12, then automatically the metal removal rate is keep on increasing. Once it crosses the 12 grams per minute, then automatically the effect or the capacity of this abrasive flow rate is reducing, so that the metal removal rate is also coming down. The graph is indicating the same thing. However, with further increasing the abrasive flow rate, the abrasive flow velocity goes down. It is decreases the abrasive flow velocity, causing reduce the metal removal rate in grams. And this is the effect of nozzle pressure. And here also the effect of nozzle pressure on metal removal rate in volume is shown in this figure. So if the nozzle pressure is increasing, the metal removal rate is also increasing. Means the kinetic energy of abrasive particles is responsible for the removal of material by erosion process. As abrasives must be impinges on a surface, work surface with certain minimum velocity so that erosion takes place. The maximum velocity for machining of glass by silicon carbide particles is 25 micrometers, and it is found to be around 150 is found to be around 150 meters per second velocity. Sorry. Now coming to the mixing ratio, means how much quantity of this air is mixed with the how much quantity of abrasive particles. This mixing ratio is very much important. It also influences the metal removal rate also. See here, the mixing ratio of 0.268 and the standoff distance with this mixing ratio. See, this is the mixing ratio 0.095, 0.148, 0.201, 0.268. Means whenever the mixing ratio is increasing, then automatically the volume of metal removal rate is also increasing along with the standoff distance is increases. So if standoff distance is increases along with standoff distance up to this 16 mm, you are going to getting the maximum metal removal rate at 0.095 mixing ratio. All these are the mixing ratios. So at 16 mm, almost all we are going to getting the metal removal rate. But if we still increasing the standoff distance, then automatically the metal removal rate is coming downward direction. Now coming to the process capabilities of this abrasive jet machining. Although abrasive jet machining gives low metal removal rate approximately 0.015 centimeter cube per minute, but it can easily produce intricate details in hard and brittle materials. Even though the machining metal removal rate is less in abrasive jet machining, but it gives intricate details in hard and brittle materials which are not possible by conventional machining process. The production of narrow slots such as 0.21, 0.1 to 0.25 mm or low tolerance plus or minus 0.2 mm, good surface finish 0.25 mm to 1.25 mm and sharp radius 0.2 mm on machine edge are some of the characteristics of abrasive jet machining process. Steels up to 1.5 mm thick and glass up to 6.3 mm thick have been possible to cut by abrasive jet machining, but at very low MRR and large taper. These are the somewhat limitations while cutting this glass. The process has a special application for machining thin sectioned brittle materials, particularly in the areas which are inaccessible for conventional machining process. So wherever it is not possible to cut by conventional machining process, there we can use this abrasive jet machining process effectively. Coming to the applications point of view, abrasive jet machining is useful in the manufacturing of electronic devices, deburring of plastics, making of nylon and Teflon parts, making on electronic products, marking on electronic products, permanent marking on rubber stencils, deflashing of small castings, cutting titanium foils and drilling glass wafers. It is also used for engraving registration numbers, and on the toughened glass used for car windows. This process is also used for frosting glass surfaces and cutting thin section fragile components. Coming to the limitations, advantages and limitations of abrasive jet machining. This abrasive jet machining, in which a high velocity jet of abrasive particles is made to strike on the surface of the workpiece for the removal of material by impact erosion. And this process is favorable for removing various deposits and coatings on metallic and ceramic surfaces. It can be also applied for cutting and drilling operations. However, the process is not suitable for every type of materials. It is preferred for hard substrates or materials. The various advantages and disadvantages of abrasive jet machining are elaborated in the successive sections. A list of pros and cons of abrasive particles are depicted below. So these are the advantages and disadvantages. Like this abrasive jet machining is suitable for removal of deposits on oxides coatings, and this sorry, the wide range of surface finish can be obtained. The process is independent of electrical and thermal properties. Even though it is a non-conductor, we can easily cut by means of this abrasive jet machining process. No thermal damage on the workpiece, suitable for non-conductive and brittle materials, and low capital investment. Coming to the disadvantages, not suitable for soft and ductile materials. Abrasives are not reusable. Abrasive collection and disposals are problematic. Tapered and stray cutting and similar effects for drilling operations. A limited nozzle life. Sorry.